Greetings and welcome, friends. So, per usual in geometry class, we have defined some concepts. We've defined them well, and then we've discovered some properties about them, and we find some theorems as a result. So we've talked about chords before, and recall. Let's see. Let's think back to a time much more pleasant. A couple days ago, when we learned what chords were. It was a segment with endpoints on a circle. All right, and because its endpoints lie on the circle, any chord divides the circle into two arcs. Now, question. All right, this is a line, right? So this is like 180 degrees here because it's a line. Does that mean the measure of this arc is 180 degrees? No, right? Because the measure of the arc would be corresponding to the measure of its central angle, right? And this chord, although it has endpoints that form that arc, do not, it doesn't meet at the center of the circle. So anyways, so that was a side note. Whoa, deleted a little too much there. I got carried away with my undos. Let's see, it says a diameter divides a circle into two semicircles. That makes sense. This is 180 degrees, and this is a central angle. So yeah, so those are going to be semicircles. I like it. All right, any other chord divides a circle into a minor arc and major arc. Excellent. So we had just done some Geometer's Sketchpad experimentation. We alluded to this theorem. It wasn't a solid proof per se, but here's some theorems. It turns out, in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Wow, that's interesting. So if you have any two chords on the same circle or congruent circles, and those chords are the same, they're congruent, then the arcs that they intersect, specifically minor arcs, will also be congruent. Interesting. Is that believable? I'm assuming we could explore that possibility, yeah, and see whether or not. It seems like the major arcs would be as well. Unless, are they worried about like the case of semicircles or things? Yeah, I don't know. So anyways, yeah, don't worry about it. So guys, the reason this is true, check this out. It's actually going to relate to, imagine my drawing these triangles here. These yellow segments I just drew, what are those in terms of the circle? What type of segment are those with respect? Those are radii, that's right. And by definition of radii, those are the most congruent to each other they can be. So that means these two triangles are congruent by who now? Side, side, side. And if those triangles are congruent, then these angles are congruent. Those aren't vertical angles, necessarily, because this is like off, those were non-parallel chords. But why are those angles congruent? CPCTC. If those triangles are congruent, then its corresponding parts are congruent. If those angles are congruent, their measures are equal by def of Kong. Those are central angles because their vertex is at the center, and therefore, like kind of some transitive property, these chords, or these arcs rather, are going to be equal to each other as well. So there's one theorem, congruent corresponding chords theorem, CCCT. I don't know. And then we just discovered this one a little bit with Geometer's Sketchpad, perpendicular chord bisector theorem. It says if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord. Okay, so it bisects the chord, so these two are equal, and it bisects the arc that chord forms. All right, so that means these two arcs are also going to be congruent. They're both the same in my case. Yeah. So that's pretty cool. The reason that's true, let's say I draw this little triangle right here. All right. This is congruent by reflexive property. These are right triangles. These right angles are congruent by right angles congruence theorem. Why are those two triangles congruent? Well, looks like side angles side, because I haven't proven this part yet, and that's regarding the arc and not that side. So if those triangles are congruent, then these hypotenusae are congruent. I can't even label them that small. And those are congruent chords on the same circle, and then by the congruent chords, congruent corresponding chords theorem, then those arcs are the same. Yeah, quite a bit of work, but it jumps from one to the next. Isn't that lovely? Lovely. Yeah, I love it. I love it. And then we also have a perpendicular chord bisector converse. And this one's actually interesting. This one might save your life someday. I'll talk about that a little later. Actually, or it might be part of your homework. I'll have to look. It says if one chord of a circle is perpendicular, is a perpendicular bisector of another chord. All right, so if I draw a chord, bisect it, perpendicularate it, then that chord, the perpendicular bisector, is a diameter. So if that's a diameter, then that means it passes through the center. So that's kind of a cool outcome if you needed to find the center of a circle and you didn't currently know where said center was. Interesting. Yeah. So let's do an example. In the diagram, circle P is congruent to circle Q. Whoop-de-doo. It says FG is congruent to JK. All right, so those are congruent chords on congruent circles. It says the measure of arc JK is 80 degrees. Find the measure of arc FG. Thoughts? Yeah, these arcs are going to be congruent to each other by the congruent corresponding chords theorem, and then by def of Kong, right? Measures will equal each other. Wow, amazing, right? You guys are amazed. Let's throw some algebra in this mix. What? Classic move, geometry. Classic move. Here, let's see if I can scale this down so that those, let's see, are those about the same? Yeah, that's close enough. All right. Using a diameter, find HK. Thoughts? How could I find HK? Yep, that diameter is going to be a perpendicular bisector of that chord by the perpendicular chord bisector theorem. So yeah, so this is also 7 over here. It bisects it, and then yeah, total length is 14. I like it. All right. What about the measure of arc HK? Well, since this bisects that, it bisects the chord as well as its arc. So what's the equation that I can write? Yeah. So that's not a semicircle. It looks like a minor arc. I think I could say minor arc with confidence there. Subtract x from both sides. Algebra. Yep. And then divide both sides by 10. 10. All right, x equals 7. But that's not what they asked, friends. It looks like the measure of arc HK, that's going to be 7 times 11. I could do 7 times 11 plus 7, 70 plus 7, or I could just double this. I think I like that idea better. So 2 times 77. What's that going to be? 140 plus 4, 154? Yeah. Sorry. I wonder what happens if you work in base 11, if that would be just a completely different world for you rather than base 10. No? I don't know. But anyways, no. Different things, yeah. We'll talk about it later. That's not even rulers measuring feet and inches still actually operate off of a base 10 number system. Because when you count to 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then hit 10, you reset the ones spot to a 0, and you put a 1 in the tens position. If you count, right, 98, 99, 100 inches, right, you reset 99, both of those spots become 0, and then you add a 1 to the hundredths place. So in powers of 10, you are counting and then getting new batches of numbers. Your digits are all based off of tens. Look up binaries someday. But anyways, for this video, using perpendicular bisectors, it says 3 bushes are arranged in a garden as shown. Where should you place a sprinkler so it's the same distance from each bush? What? 1 sprinkler. Well, check this out. Let's a sprinkler, we're assuming, is going to have some sort of circular pattern is what they're describing. If I draw this chord and this chord, a triangle, and then what would the triangle do? No. It wouldn't be here. Well, check this out. You guys, actually, if you want, you can follow along and draw this on yours or estimate it on yours. There we go. Here we go. Here we go. So I'm going to construct some perpendicular bisectors. I'm imagining that these 2 segments that I've drawn will be chords on my circle. And so if I have perpendicular bisectors, what would I know about the line that passes, or that is a perpendicular bisector to that chord? All right, so there's one. And what's that place going to be? What's that place called? I need a little larger on that one, don't I? You're thinking like, yeah, triangle speak, but actually, yeah, you're kind of right. These would relate to, yeah, it's going to be the center of the circle, because these purple segments, or lines, this purple line that I drew, is going to be or contain a diameter of a circle. And if I draw them, right, and I have 2 diameters that intersect each other, the only intersection that 2 diameters can have is the center of the circle. All right, so well, let's find out. Is this the center of the circle? I mean, I've had to estimate the center of each shrub here, you know, on its own. But yeah, so that ends up being the center of the circle that has those as its chords. So what do you know? There you go. Hey, how about another theorem? How many theorems are we up to? 9 already. 9. Yeah, I know. Yeah, we're only on... Yeah. It might be 20-something. I don't remember. It says, in the same circle, Or in congruent circles, two chords are congruent if and only if they are equidistant from the center. All right, so if it's if and only if. So yeah, if I have two chords that are equidistant from the center, then the chords themselves are going to be congruent to each other. Or if I have two chords on the same circle that are congruent, they will be equidistant from the center. Distance to the center would always be measured perpendicular from those lines respectively, right? So, guys, I like these problems. Here we go. Look at example 4. This thing's golden. Delicious. Delicious math problem right here. All right. In the diagram, QR equals ST equals 16. All right, so QR, 16. ST is 16. All right. And then they said CU is 2x and CV is 5x minus 9. It says find the radius. They changed it up here. Look out. That's the radius, I said. We'll make our radius purple once we know which one we'd want. So yeah, so what can I do? Where do you guys think I can go from here? Can I find the value of x? Yes, and that is true by the equidistant chords theorem, and what student had said is 5x minus 9 equals 2x. So let's solve this for x anyway. Hopefully that helps us find said radius. I like this problem. This problem's good. We've got one like this on the test as well. Yeah, this problem's got like a few layers to it that are just wonderful. So I get x equals 3. And so what is this blue distance? 6. All right, so that blue distance is 6. Now, if I want to find the radius, you might be like, okay, I guess I need to find WU OTI, am I right? Sorry. So sorry. No. I was just so excited. Don't worry about it. Oh, it's mine. You can have it. I didn't drink it. It's unopened. I got it from the interview committee I was a part of the other day. I 100%. You're welcome. Yeah. So this is 6. Now let's look at the following. So this you might think is a good radius to go for. Actually, maybe I'll have one of you try to find it that way. If you could show me. Yeah, there's ways you could do that. So here's a radius, but that is not the most helpful radius to work with here. Remember, any point from the center to the edge of the circle will be a radius. Does anyone see a better point to go to? Yep. Q to C. Yes, yes. That's the radius that I was thinking of as well, yes. Let's see. I gotta be careful. All right. Remember, every point on the circle that connects to the center will produce a radius. So this is the radius. This also was a radius, okay? It was just not as helpful. So yeah, so if this is 16, QU is 8. This we knew was 6. Does someone know the value of R right now? I wrote it so wrong. Is there anyone that, is there a way looking back that you could have answered that more quickly? Yeah, it's a ratio of 3, 4, 5. No. But it's doubled, right? So that was going to be a 6, 8, 10. So yeah, 10 was the value. But that doesn't matter. Not all the time will it end up being a convenient Pythagorean triple. But yeah, the way you would find the radius is by drawing from the center to the end point of one of those chords. and that would help you out. Quite nice. I really like that problem because it's not immediately obvious. Well, all right. Well, thanks for watching, mis amigos de internet.